Hello, how's it going? Do my knuckles look sore? I just got back from boxing. Yo, when people do orient their designs but not around data, I start punching. Okay, right. So I've been looking at my little data oriented engine thing and shifting that over to C++. And I've been trying to address the issue of containers for data. Of course, C++ has a standard unordered map. Okay, I swear, last tangent, but I've been watching CppCon videos and they're all so cult-like, and everyone's calling standard classes stood, like stood unordered map. That's crazy. I sort of have no respect for language when it doesn't, like, I'll change abbreviations around and stuff. I call it CLang, not clang, and I'm gonna die on that hill, right? Okay, so STD is an abbreviation, a shortening of standard, not stood. That's a different word. Okay, back to the main thing. So we have standard unordered maps, but they're just a little hand wavy for my liking in the underlying hashing function and memory layout. And I like vectors. So ultimately, I want some data structure which is contiguous in memory and I can just stride through it. So here's what I'm proposing. And this is sort of an open question. Like, I'd really like to see your comments on how you think I should address this. But here's what I've got. I'm going to make a basic container that has some underlying, we'll call components. Okay, so there's an array there, and we have component A, and so on. And these components can be chunks of data. So if it's a transform component, for instance, it would be each of these would be structs holding both a vec3 for position and rotation, for instance. Just some sort of underlying object that is contiguous in memory. And then we have entities. And this is just a list of, or a vector of unsigned integers. They are the IDs of these objects. So for instance, if we were to swap object A and B, of course, we'd swap the components, but we would also swap these entities because there needs to be a one-to-one mapping on the position. Okay, so there are a few things to consider. First of all, how are we going to use this component? Well, in two possible ways. Take, for instance, we have an update, a set of update components, and then a set of transform components. The CPU will essentially be stepping through one by one each of the update components, but not everything that has a position and rotation will be moving around. So then we'll need potentially random access of these elements. So we need two things. We need to be able to step through it one by one, and we also need to be able to search things really quickly. So there are two possibilities. The first possibility is unordered, and that is when I insert things, I just insert them on the end. I don't track any order, and we'll say, all right, so clearly we can still scan through these things and they're right next to each other in memory, so that's nice and fast. Then how long would an insert operation take? We'll go insert, delete, and search. So to insert, that is pretty much a constant time operation. We just push back. Remember, with standard vector, when you push back, it uses a doubling strategy, at least a doubling strategy, actually, according to their documentation. And so that amortizes out, that averages out to a constant time operation. To delete, that's also a constant time operation. If we want to delete this thing here, then we just flip it with the last element and then decrement the size by 1. That essentially forgets about it. And then to search for a particular object, that's ON. So for instance, if I'm searching for something right at the back of this array, I'll have to look from the start until I find it, because these things are completely unordered. Now, on the other hand, let's say that we maintain some sort of order in these objects based on their entity. So if this is like 1 to 5 or something, and then I insert entity 4, well, then we need to search in and insert it in here and do the same sort of thing. So we'll go through these. Okay, so to insert potentially is an ON operation because we may have to rejig a whole bunch of things. We may have to shuffle everything to make room because we want to get it in the right spot when we add a new object. And similarly, now when we delete, we can't just swap the back and the end because we care about maintaining the order. And if we just randomly swap things, order is not going to be maintained. Now, there is one caveat to that, and that's that with the methods that I'm using, these things will have early exit cases. So you could be saying, oh, wait, my college told me about merge sort, and that's log n. Well, the issue with that is that it has no early exit case. So if we have an array which is mostly sorted, but just one or two elements around, we still have to go through the full merge sort, which has overheads and things. So that's not great. But we get one benefit, right? So far it's not looking too good. We get one benefit, and that's that we can now use binary search to get a given component corresponding to a given entity. So here I say log n. If you're not familiar with math, what are you doing? But the basic idea is that with binary search, we're always halving the size of our search space. So for instance, if I have 8 objects and I'm looking for a particular thing, if I keep halving it, I can only halve it 8 times until I get down to a single element. So in the worst case, it'll take 3 operations or something. Compare that to ON, in the worst case would take 8 operations. And the way logs work is that if I square the number of elements, then the number of operations only doubles. So it's really, really good performance. Sort of the gold standard for a lot of algorithms. They all try to get logarithmic. Now, as an example, I'll look at binary search on a mathematical function. So let's say we have some sort of function. Somewhere its value is above 0, somewhere its value is below 0. And we want to target the root. So we want to find where it's equal to 0. We start with 2 guesses. Okay. And then we evaluate the value there. And because this function is continuous, let's say if the value at x equals a, less than 0 and bigger than 0, but a quick way that we can check if 2 numbers have opposite signs is to multiply them together. And then if the result is bigger than 0, then these 2 numbers are opposite signs. Okay, so provided that condition is met, we have a guarantee that there's a root somewhere on this interval. There could be more than one. I don't know why I'm talking about mathematical binary search when I just need to do an algorithm. But anyway, the next thing we do is we guess midway between the 2. And then we evaluate, is this the product of the values on this interval? Is that less than 0? In this case it is. And that tells me I know that I can move this B up to my C position. Okay, now I'm going to be a little dodgy here. This isn't quite halfway, but I just want to show the A case. So then I go halfway between, pretend, halfway between, and then I say, okay, well, is the product of these values less than 0? No, it's not, because we have negative times a negative, so that's positive, the product of those two, and so the solution is somewhere here. And you keep going and going and going. In a mathematical sense, it doesn't really converge. It takes heaps of steps to get within a given tolerance. I'm rambling. In a programming sense, it does converge, provided that the thing we're looking for is in the entities array, which we can guarantee because we designed the thing. Okay, so let's have a look at how I implemented this. Sorry, just before we have a look at how I implemented this, I wanted to talk super briefly about why I preferred this option to this option. And like I said, it's not perfect. Let me know in the comments. I really love your input. But my reasoning here is that, at least in my systems where I'm using it right now, I am inserting and deleting very rarely, whereas I'm searching up random things every frame many times. And so because I'm doing this operation a lot more per frame, then this is sort of the critical thing to care about. It's difficult. Very rarely will you have a perfect environment. I make decisions every day that send millions of clock cycles to their death. It's just, that's the fact of it. Now, Having said that, I will briefly talk about another data structure, which is a balanced binary search tree. So the way a balanced binary tree works is that we have a node, and the thing on the left always has to be less. Let me go 3. And it works recursively. So the thing on the left always has to be less. The thing on the right always has to be greater than. I don't know. Let's do that. Okay. Now this structure does have log n for everything. So it's log n to insert, it's log n to delete, and it's log n to search. But it has a downside, and that is the underlying memory layout. So the way this works, if we were to represent this in if we were to represent this in an array, is we have the root element there, and then the left and right, and then we sort of go from there. This is it's been a while since I did this stuff, but something like that. There might be other ways. Let me know in the comments. It's been so long since I've done this thing. Probably like pre-order, post-order? One of those traversals would actually... What am I thinking? Okay, so there's that. But then the issue that I'm getting at, and I'm just doing this on the fly, but the issue I'm getting at is that if we have a layer... Okay, let me put if we have some layer with just one node, for instance, this whole bottom layer still has to have memory allocated for it, at least if it's the way I'm thinking. And so that means that the data wouldn't really be tightly packed in the bottom level of the tree. And that would be pretty much equal to, or almost equal to, everything above the tree. So you have half the data structure is nice and packed, potentially half the data structure is just wasted space. So for that reason, I didn't look into this. But as I say this now, that might be good. Anyway. All right, welcome to Linux land, Ubuntu land. I will be providing the source code for this, although be aware that whereas my previous videos in the series were Python, this one's C++ and CMake and stuff. Also, it's the source code from my OpenGL tutorial. Okay, so here is my solution. I'll step through it. I really did try to keep it as understandable as possible. So, right up the top, I'm defining this generic template class. It's basically going to be a container of whatever I want it to be. Okay. We have binary search. I'm actually going to leave that, talk about that last. So we have a vector of components and a vector of integers, which are the entities, the IDs, corresponding to those components. We can insert. Okay. Now this is a little dodgy, what I'm doing here. And it's basically because what I guess what I would like to do is resize, but my components, may not necessarily have a default class, so I'm doing this for now. It works for my purposes. Okay, so basically what I'm saying is we increase the size by 1, just pretend I did that, and then we step from the end, and every time we see an entity that's bigger than what we have right now, we shuffle that along. So we keep stepping along, moving all the entities which the IDs are larger than what we're inserting. And then by the time we break out of this, I will be in a position to correctly insert the entity and components in place. That's it. It's just a simple sort of insertion sort. Actually, insertion sort's something different. But anyway. Okay, so how do we remove? Well, we want to remove the component corresponding to this entity. So what we need to do is we need to find where that entity is in both of our vectors. The positions will be the same. So we do some sort of search operation to find the entity that we're after. and then we erase that position both from the entities and components. Done. It's gone. C++ will automatically shift everything forward to fill that space. Okay, how do we get a given component? So you tell me, hey, I want the thing for entity number 3. All right, so what I do is I search my entity list for that entity number 3. I have this query object, which has a position and a flag, which indicates whether it was successful or not. I won't worry about that, pretend everything succeeds. I will just use that position, fetch the corresponding component, return it. Okay, so on to the binary search. So this is the big thing which really accelerates the structure, the ability to binary search. So we have this position. This is where in the entities vector the given entity is found, and then the flag. Now flag basically indicates whether it was successful or not. So I'm using -1, 0, and 1. The reason for that is I tested this on numbers up to like 1 billion, and beyond a certain point I found that I would get integer overflow, and so I'm just going to cap it. So 1 means that this entity that we're at is above our target, 0 means we're exactly on the target, -1 means we're below our target. That's really all the info we need. Okay, now, little funky, but we start position A at the front of the array, basically, position B at the back of the array. We do want to test for the case where we hit it straight on. So we set the flag. Remember, the target is this entity here. So if we take the entity in this position and then subtract our target, if it matches our target, it's 0. If where we are is less than our target, this will be a negative number. If we're above our target, it'll be a positive number. And then I simply need to clamp that between 1 and -1. Hopefully that is not... no, I think that might be using conditional code. Anyway. Right, so if it turns out we hit it dead on, just return it, we are done. Same thing with B, same logic here. Okay, so what we're doing down here with this while loop is 2 checks. First of all, we need to have a range which is bounding our target. So we need to have a guarantee that our root is somewhere between these two, so to speak. And then secondly, if A and B are right next to each other, so they have a difference of 1 or a difference of 0 or something, then, okay, maybe a difference of 1, then every time I try to subdivide, we can't subdivide between 2 numbers which are right next to each other in a discrete case. And so this is just checking that our start and end have not converged and run into a single point or 2 neighboring points. Okay, so subdivision. We take the 2 positions, take their average, okay, and then we test for the value at that midpoint. All right, again, we need to check if we've hit it straight away, we're done, return it. Okay, now on the other hand, if the target lies between A and C, then the product of their flags will be less than 0. In that case, we know that we can take that C as our right bound. So our right bound shifts to the center, and then we just go on, do the next step of the iteration and keep going. Otherwise, we know that our solution, our target, must be between C and B. And so A comes up to C. Okay. Right, so we do that stuff. We get out to the end. I don't know, this indenting is a little funky, but C++ doesn't care. Okay, so if we get to the end, then possibly we still need to check whether we've hit it. So if B, we iterated, whatever, and it turned out B was actually right on the money, okay, then just return B. Otherwise, return A, and I don't care about checking whether A worked or not, because something has to happen. Because I'm designing the engine and I'm going to guarantee that the entity is always there. Maybe if I want to, I can add error checking, but I'm happy with that. Okay, so that was my super not over talking everything demonstration. And let's look at the actual demonstration. It won't be too exciting. This is the same OpenGL demo scene that I've been doing with a bunch of other things. But there we go. We have this. It's using my custom data structure, and performance is about the same as it was using an unordered map. But how could performance be that different? I mean, we only have like 3 objects in our scene. Anyway, that's it. I guess, like I said, code will be provided if you want to see how this is used as part of a larger project. But yeah, hope you enjoyed that. All the best, and I'll see you again soon.